So for today, what I'm going to talk about are some parametric design processes, trying to get at the theory of how you put these things together. So I'm going to give you some examples today that are going to be showing you some of the patterns that we've looked at, refreshing your memory. These are all things that are going to be relevant to the projects you're working on right now. Tweaking them a little bit, seeing them in a new context that might help you. Okay, so I'm going to be recording this today for you guys, so you'll have access to it later. So don't worry about trying to scribble down exactly what's going on. Just focus on what I'm doing and ask me questions if something seems unclear. I won't give you the answer to your project, but I assure you it's in here. Okay. What I'm going to do is I'm going to take a step back to last week and look at some of these examples that I already showed you, which have patterns that reoccur in your current projects, and go through some processes for how you might attack these. Okay. Before I actually get into that, there are a couple of things that I want to show you. A couple of different commands that I haven't taught you, but that I realize are probably going to be really helpful when you guys actually have to make these. So you can make the patterns, you can make lines, you can make surfaces, but I think the missing component is making solids out of things, right? Like when you actually get these in a Rhino, they need to be solid objects, okay? I've shown you things like, again, making surfaces. I showed you guys like the pipe command. Like those are the kinds of things that you're going to need in order to actually get these things to start to look like buildings and not just like abstractions. Okay, so I'm going to show you a couple of things. First, I want to review one which you might have missed, and that's the extrude command. And extrude basically takes a profile of something and you extrude it along a vector, and that essentially gives you a surface. Okay, and you guys are familiar with this from Rhino from like second year, but maybe haven't experimented with it parametrically. If you guys remember the example that I showed, I gave you that like facade example where I made I took a couple lines and I lofted them together, and then I got a surface, and then I extruded that. And that's something that I want to point out. So this is a surface that I just made here. A very tiny one, apparently. All right, there we go. So I got surface, and I'm just going to reference it. But you could assume that this would work with any surface you create parametrically. Okay, so I referenced it. If I plug the surface in, I can also extrude it. Okay. So I need a vector. If I look at you can always look at your compass on the bottom here to understand which vector. And if I want to make this thing go out in this direction, which of the vectors do I need? X, Y, or Z? Y. Awesome. You guys are great. Okay. Y. You know what you're doing. So if I put Y in for the extrude, and you'll notice that it actually extrudes maybe the opposite of what I want. That's because this is positive Y, if you see Y here. Okay, so if I'm thinking that this is the face of my building, I actually want to extrude it negative Y. Okay, so I put a number slider in, and I just make it a bunch of values that are negative. So let's just say -10 for the value. Plug it in, and now as I go down, it actually goes out. Okay, so one thing that's really useful to know is that if you take some curves and you create a surface with a loft or something, you can extrude that, and that becomes a solid. That is a six-sided box. Okay. The other thing would be if you had some geometry that you made, and again, I'm just going to create something like arbitrary, but let's assume that you used some points to create this object, this sort of like parallelogram. Okay. Got to go ahead and delete that, and I'm going to reference this as a curve. So if I have a curve, and I'm extruding in the Y. This is another thing too. If you run into these bugs like this, right, it's not extruding in the direction that you think it ought to, you want to check that vector. Okay. This one, in this case, I want a Z because that's the flat side that it's flat on. And I've done this in the negative, but you get the idea. Let's go ahead. So what happens with this one, though, is that if I extrude a cross-section for something, if I extrude a curve, it's not capped. Okay, it's not a solid. It's four-sided, or like whatever sided. It doesn't get a cap. So I couldn't if I put that on my model, it's not going to look right? It's not going to have like a solid like profile. In order to do that, to fix it, all you do is just throw a cap holes component into your sketch, and that actually gives you, that caps the holes, basically. Okay. You might run into some bugs if you do some really complex surfaces. If the top and bottom are not flat, you can't cap it. It won't wear a cap. Okay? You got to do some other stuff for that. But most of the things I would assume that we would try are going to be flat, and cap will work for you. Okay? What you end up with is a closed B-rep. And B-rep is a boundary representation. I think I talked about that in the video this week. That's all that means. And a boundary representation, right? The representation of a bound, that's a solid. Okay? Or that's some kind of object, basically. So, so don't forget extrude in the things that you're doing. Like, some of you guys need this extra step to make the pieces that you want. Extrude works on surfaces, it works on curves. Okay. The other one that I want to talk about, and I know I haven't talked about this one, is sweep. I'm gonna go ahead and kill that. So sweep is kind of like a loft, only a sweep works with one cross-section, or I guess multiple cross-sections, but along a line. So loft tries to like morph between different cross-sections. A sweep sweeps a profile along a line. Okay, so you get sort of like, you might, it might be like a miter. I sort of make the analogy, it's like when you push like the Play-Doh through the little thing, and you get these little, you know, like sort of like these tubes of Play-Doh that are star-shaped, or, you know, something like that. That's kind of how a sweep works. So if you throw a sweep out, sweep one. There's one project in particular I think that really needs this. I think I've talked to all the groups about it. So sweep takes a curve, and the rail curve, this is the rail that we're going to sweep the thing along. Okay. The section curves are the curves that we're going to, they're the little Play-Doh mold that's going to get pushed through. Okay, that's the section. And then this whole like trim at kinks, don't worry about that for now. That probably won't really come up. Okay, that just means that if you had a line that has kinks in it, it's gonna chop that section at each one of those. It gives you it gives you the profile that you probably want, but it's probably buggy. Don't take my word for any of this. You really do need to just try these things, like play with them, so that you understand what they are, and that you make your own explanation for what that is. Okay, try it with trimmed, try it without trimmed. Okay. I can't show you all the details, so you have to kind of experiment. So we're going to reference that curve. And I always hide them just so I don't accidentally like select them or something. And that's going to be our rail. And the section curve. Section curves have to be aligned in the direction that you're going to be like, you know, like pulling them. So if let's do a star or something. Let's do polygon. Let's something fun, I guess. I'll do a polygon. Okay, that's an odd section. And so I take the polygon's what I want to pull. First of all, the polygon's like actually kind of huge, so I'm gonna need to scale that down a bit. Radius. There we go. That's already like better. Okay. And if you plug this in, you would get this weird limp kind of flat noodle thing. And Nick, what did you sell me here? This is really broken. Okay. But what you got to do is that right now, first of all, this shape is not like on the end of this. And second of all, it's not aligned so that you can push the Play-Doh through, right? That's why that is the way it is. You got to get it there, okay? So you do two things. You take the curve, and I've shown you guys this before, I think, but there's an endpoints component, which I find very useful. You put any curve into it, and it gives you the start point and the end point as sort of like a plugin, okay? And so what I can do is I can plug those in, and then I can put a plane on this. And I think I want like a ZX plane. Let's see, I always do this backwards, XZ plane. And what I want to do is I want to put a ZX plane at that start point. Okay, and then right when we have a plane, I'm gonna back this up here. When we have a plane for something, we can change the position of it, and that's what we're gonna do. We're gonna reposition the polygon on that plane. And there we get our noodle. And it's parametric. Okay. So, you know, you can think of all kinds of strange things that you could do with that, right? But some of you guys, if where it's really useful is if you just want to make like a steel member or something, or like something that you would get like at Home Depot, and you want it, and you just want even to make like a diagonal member, take a rectangle or a square and sweep it across a curve, and that's like a buildable like bent piece of steel or something, right? Okay, that's where you'll find it really useful. And in fact, I mean, again, this is the great thing about parametrics, is that if I have that, I can could do any number of polygons I want, any sides, and now 2's not going to work, but so triangular, square, 5-sided, 6-sided, again, parametric, right? So if you put a rectangle on it and you align it properly with it, you can perform a sweep, and sweeps don't have caps on the ends of it. So if you throw a cap on it, that's going to give you something that you can 3D print, or that's going to render correctly, right? It's going to have all 6 sides, or all whatever 12 sides, whatever this thing has. Okay, so cap once again. So just think about that. If you need a square section to do something, right, for a window mullion or for whatever, you can do a sweep if you have like an angle or some kind of a curve or something. If you just need something that's straight up and down, sweep doesn't really make a lot of sense, right? You just want to extrude that square up and down, or in and out, or something like that. Okay. Sweep is really useful for odd angles. Okay. So I just wanted to give you guys those because I think they come in handy with some of these projects. And I know I didn't talk about sweep. You may have forgotten about extrude, but it's really useful. Let me make sure my notes here. Yep, cap, extrude, sweep. All right, covered. Okay, so we'll see these a little bit today, but I just want to introduce those to you. So to start talking about the parametric design process, I want to start with this example because I think it's pretty simple, but it has a lot of elements that we have seen, which is basically like repetition, but it's a staggered. There are some that are extruded and there are some that are not extruded. Okay, so let's kind of refresh ourselves with this pattern. So first thing I'm going to do is start with a reference surface once again. So make something. And you want to make these things fairly large when you do them. It's easy because there's no scale inside a Rhino to just make something that you think is a pretty decent size, but it turns out that it's only like a foot across, and then all your sliders have to be minuscule for it to work. Okay. Try to make it, if you can trace the drawings that you have and get it to be roughly the size of that wall that you're working with, that's really helpful. Because then you can use the drawings that they give you to figure out what the sizes of those panels are or of those windows. Okay, I think that's helpful. So this is a really powerful pattern, and I really want to refresh your memory about this. I think we talked about this in week 3, but this is the surface division pattern. And basically the way it works is you take a surface and you're going to reference it, and then you have the subdivide surface, which is, it's like called an isotrim, but then it says subsurface. It's really difficult to follow why they would name it 2 different things, but anyway. And then you want to divide domain squared because we're actually going to divide the x and y domains of this. And you plug in your surface, and then this plugs into the subsurface. And that's going to give you the ability to divide any surface into any number of cells. And these UV controls are parametric. So let me go ahead and throw a couple of these in here. And maybe I'll actually name them today. Whoa. A little HTML in there, okay. V, okay. And a really long slider for no reason, okay. Let's fix that. Okay, so U and V. And you know, if you have 0, you don't have anything, but this way you can control the number of divisions. And this will work for any arbitrary surface, as I've shown you. So if you have some wicked curve or something that's like a vault or whatever, it's going to divide that up. It's extremely powerful. Okay, and a lot of you guys basically just have walls that are panelized. Okay, so this is not a bad starting point. What you're doing here with this is cutting up the surface into multiple surfaces. You have one surface, which I'm going to hide, and then you see the output here. It says 156 surfaces. It's 13 times 12. Okay, so now you can grab each of those surfaces and you can extract things from them. And one of the patterns I gave you guys that was really useful is to just drop an area component, and then you get the center of each of those pieces, right? And so that can be a place for you to distribute geometry in your projects. Okay, with this particular project, I just showed you something, right? With extrude, I can extrude those panels out basically. Okay, I can take the surfaces that I cut the thing into, and I can extrude every other one. Okay, and so that's actually what I'm gonna do here. So this is one example, and the advantage of starting with the surface is that if I adjust the surface, if the design is based on this, then if I'm using a surface, that's going. If I change the surface, then the design changes. It's not the module comes from the surface. Okay, I'm going to show you some other examples today where I take the module and I build up the surface. Okay, but I want you to see how the two things are actually different from each other. Okay, so in this example, I don't need this area component at all. It's not the game we're playing here. Okay, so I have a collection of surfaces, and what I'm going to do, and you'll see this a lot here, is I'm going to throw a cull pattern on these. And a cull pattern, it defaults, it has this like false, false, true, true. I'm going to make it false, true. And you get this. And now, cull patterns have some like bugs that you have to watch out for. Okay. One, remember we said that there's a difference between culling a grafted set and culling a flattened set. We don't have to worry about that here. But if you get these kind of banding, I want a checkerboard and I'm getting banding. Okay. How do I fix that? It's not that this part's right. The true false is right. The issue comes from the way that I parameterize that, right? If there is an even number there, then they're going to look like rows. But if they're odd numbers, I'm going to get that on-off pattern. Okay, just because of the simple math of it, right? When the row comes along to the next row, if you have even numbers, they're going to align with each other. You're not going to get the shifting. Okay, so as a constraint within this system, right, you need to set these up as odd numbers. I think I've shown this before, but you can say even or odd numbers only in your sliders. Okay, and that's actually going to give you the U part doesn't really matter as long as the V gives you a set of odd numbers. Okay, and you can verify that experimentally. That's something that I want to. I'll say again, but I want to talk about is that a lot of this stuff, as much as I talk about having a plan for this stuff, if you're not sure what something's going to do or what to do, just try something. Like if you see this bug here and you know that it's not working, before you like redesign the whole thing or like tear the thing apart, like play with the system a little bit to see if you can get the behavior you want, and then you might be able to figure out what the bug is. Okay, so like if I ended up with that bug there that I wasn't getting the staggering that I wanted to, okay, you need to go back and say, well, maybe it's just the parameter, maybe it's just like the data that I'm like putting into it. Maybe that needs to change, right? It's not that I used the wrong thing here, okay. You need to just try stuff. It's free to like try. You're not penalized for the number of times you try different things, okay. This is on the computer, so try that. And try to work your way through it first, okay? So what I get is I get these are now the ones that I have, okay? And I can, so I've turned off half the surfaces. And now I'm ready to extrude these. So drop an extrude component on these. But then I need, and in this case I want to extrude these in the Y. So this is actually repeating the same pattern that I had before. And again, they're gonna go backwards, so I'm gonna want a number slider that's negative. Or I could just put a value in here. Oh, it doesn't let me do that there. Maybe I can just do negative F here. That also works. So I'm just gonna make this negative. And so this is that process here. So I'm gonna go and turn off culls and turn off subsurface. Whoop, not that one. Still, actually, I don't need the divided surface anymore. I can turn off the original. I can turn on the original base surface. So now I have these extrusions, but these aren't exactly the way that this is, right? If we zoom in, there's actually a slight gap between the panels of these things. Okay. And so this is another point I want to prove, is that when you do these processes, you don't try to do the whole thing right like the first time. Like what you do is you just kind of gradually like increment this process. So I start from the thing that I know, which is how to divide the surface, how to extrude these things. Okay, I'm not worried about how do I copy this panel to these things so that it's like shrunk. I start with a kind of imperfect version of this. Like you might even say it's kind of like a buggy version of this design. Like there's a gap between what I want and what I see on here, right? But now I'm going to go in and I'm going to like I'm going to like refine that. And that might not be like a linear order through the program. I might have to go back. I might have to try a different method. I might have to like remove some things. Or that might be adding another thing to it. Okay, you just have to keep like refining the script. Okay, it doesn't come out like perfect. Not everything is going to be in it in the first version of it. You have to just keep having like an iterative process through it. So in this case, I had these extrusions, and that's and in fact, like I want there to be a gap in these things. And so one thing that I could try, you could say that I would take those extrusions and I would scale them down, right? That would be a way to do it, and that might work fine. But another way to do it would be to actually go back, and when I had my original surfaces, whoop, I don't want to do that, and I want the culled ones. Take the culled surfaces and scale them first, and then I can do the extrusion. So we'll throw a scale in there, and you know that all these things. There's a bug there, right? Because we're not paying attention to the centroids of them. So here's where we put an area in. So we get all the centers of them. And then you can put a parametric slider in for that scale. And I want these to be like 90% or so. Okay. I'm going to clean this up here. Let's see here. Okay. So we've got our scale. And now these are the scaled ones. And instead of the original ones, I'm going to plug in the scaled ones. And then unhide my preview these. There. And now I've got the gaps in the panels, and the gaps are parametric. So again, I didn't start with these and then construct the wall from them. Like these are based on the wall. Again, you could do this in a different order. Like I could have gone back and taken these extrusions and scaled them, here. But what I want to do is I want to like organize this so that if I change something earlier in the sketch, that it's going to propagate like correctly. So in this case, I could, if I change the like cull pattern, that's going to change the ones that I scale. That's going to change the ones that I extrude. But again, this is something that you could try yourself like experimentally and see which like method works for you. But I didn't really think about scaling it until after I had already seen the first round of these kind of like extrusions. Okay. And then something that you would do next week would be to say, will this work for any surface? So again, if I draw some crazy surface and I extrude this up and I plug that in for my surface, is that going to work? It looks like it. Hide this and see. It looks like it does. Let's look at it so you can see I have the gaps in it. Look at the top of it. But you'll notice something about it though, that there's kind of a bug. That the way that it's extruded, the extrusions when I did this, are only in the y plane. And so what happens if it changes planes? Like what happens if it's pointing in a different direction? That's going to change those planes. So it's not actually variable. It's not variable enough. It's not parametric enough because it can't like stand up to that. Okay. This is what you guys will do in week 3 is actually take the ideas that you have and make them work in every situation or in most situations. Does anybody know how I could fix that? How I can make them extrude in the proper direction? Monica? Not horizontal frames. It has to do with the vector that I extruded along. You guys remember the porcupine example? You had the curvy thing, and then at first all the cylinders were in the same direction, but then I did some stuff that made them flow at the surface of it. Evaluate, yeah. You do an evaluate surface and a curve on surface point, or the closest point on a surface. And that's actually going to give you the vector for each one of these panels, like no matter which alignment it is, and then you feed those like alignments into it for the extrude, and this will work for anything. So you'll get this checkerboard like pattern, you know, on like a sphere if you want to, because it's going to use the normals locally. Okay, so good. So that's the kind of idea. It's like you have to kind of look at these things and find out, you know, for yourself. Yeah, see how these things actually get like narrower because and then they get larger. You might like that actually. That might be interesting for your design. But if it's not the intention of it, the fact that they project outwards, you need to go back and edit that script. But you can't do that until you figure out maybe how it works on a flat surface. Okay, because it's easier to figure that part out. There's less stuff. Once I begin to add the components to make this thing work on any surface, it's going to get twice as complicated. Okay, so again, don't attack the whole problem at once. Like start from like what you know and what you need, and then begin to refine it gradually. Okay, take your time with these things, like I say before, and really like slow down and try to keep your space kind of organized. Because it's really important to understand like the order of this thing so that you can get the right state of the model. If you mess up the order, you're going to get bugs. Okay, so that's a really quick example, but I wanted to remind you about those kinds of patterns. Okay, I'm going to show you guys something that I think a lot of you guys that'll be useful to you. So some of you guys have these like row patterns. Let me go ahead and Moodle it. I'll show you what I'm talking about. So just for example, this piece, I think there's a couple of projects like this that have these like interlocking patterns of like a module. And in fact, there's a module that's, so there's an A-B kind of rhythm. And we've seen, I just showed you an example of using like a cull pattern to create that stack pattern, okay? But I want to remind you guys again, and I want to show you an example of how you can distribute two different objects that have a relationship to each other parametrically along that kind of a surface, okay? And then I'm going to show you another way to do it. Because I think probably 60% of them have this idea with them. Okay, and I'll show you, yeah, wait till you get there, I guess. Okay, so the same thing, I'm going to go ahead and take that pattern that I had, and in fact, I'm going to get it back. Oh, I did a new file. Okay. Well, so we'll do the same pattern again with the iso surface, iso trim, and by domain. And I'll make a note of something that might help you with this as well. Which is that you can have a surface division that is, you know, just like bands of something. It doesn't have to be like a grid. It could also be horizontal bands, okay, and that might be useful for some of your projects, okay. And again, if you have if your project is mostly vertical and you want it to adapt to any kind of surface that you can throw at it, you can just set either U or V to 1. I mean, in this case, the vertical, you want to set V to 1, or if you want bands, set the U to 1, and you get like these tiger stripes, okay? So just to kind of show you that pattern here. But in this case, I want to look at this one. And go ahead and turn that off. So this is a case where you might look at the module that you're using, and so you have the kind of distribution, and you have the parametric object that you want to distribute, okay? And the first place you might start is just to understand, I think a lot of you guys did this yesterday, was to start with the object that you're trying to make, okay? And in this case, I'm going to start with a cylinder, and I'm going to cap it, because I want it to actually have a solid. And we'll throw some sliders in there so I can get what I want. So radius.
Is there a way to change the default for these components like the slider?
If you go into the XML code and you can change it. There is. Yeah. Yeah. So I'm making kind of like a disk, okay, if you want to call it that. And what I want to do though with these disks is I want to sort of angle them. So I'm going to go in and I'm going to rotate these disks. And so I take the geometry, and we have this pattern that I think we've talked about a lot of times before, where we're going to rotate them. Actually, yeah, we'll stop with that one. Okay, and then do a radians component. K360. And I want this to kind of flip end over end, like you're flipping a coin or something. Okay, so if I do this, you know, it's not rotating in the right plane, so I need to actually change the plane. Okay, and there's 3 different ones. So again, if you don't know, if you're not sure, like try the 3 different planes. But it's already in the XY. I think I want it to tumble about the X plane, so I think I'm going to do an XZ plane. Yeah, there you go. Oh, actually, that's the opposite of what I want. Okay, so there, try the last one. And by default, YZ plane. There we go. Okay. So now I can control this thing parametrically. Okay. And that's the first bit. And I can go in here, turn this back on, and I can look at this. And I can say, okay, I want to distribute this thing on this surface. Just before I, just so I understand what that's going to look like. So I get the center points of them, and I could do something where, I take this, and I go all the way back, and I plug. Oh, and that's actually really going to be, and that's not going to work, right? Like the ordering of it's not going to work because the like rotation planes are not going to align right. Okay, so in this, I've sort of taught us that we can take points and we can use that to distribute geometry. Okay, but in this case, that's not the order that we want. What we want to do is take the piece that we've rotated into the right position and distribute it to those points. And to do that, I'm going to remind you of another pattern, which is to use like the Orient component. And the Orient takes some geometry, and it takes 2 planes. It takes the initial plane and the target plane, and it allows you to, like basically make that distribution. Okay. So what I'm going to do is that I'm going to use the same plane that I rotated it in as the Orient plane, and then I'm going to take the ZX plane, because I want these to be flat. So ZX, XZ, let's get that backwards, as the, and then actually, here's the thing, I want to distribute it to all these points, so I'm going to create planes at all these points, okay, and then use those planes as my distribution. And actually, I think I screwed that up. All right, let's do a ZX plane for this one. Maybe you like that. So just disconnect this. Obviously, I get confused sometimes. Okay. There we go. So we take it from we take the alignment of the plane that it's in right now, right, which is that XZ plane, and we duplicate that alignment along that surface. And if I go through and I kill all this stuff, I get this kind of thing. And you know, if you were really, I mean, and you could kind of nitpick this and say it's not exactly the design or whatever, but again, we're kind of incrementing through this. Like later on, you could go through, and you could add a little bit of a move and just move that cylinder over a little bit so that it touches the edge of the wall, like the way you want it to, right? But for now, it's fine. I got the idea of this. Okay. What I want to do though is I want to play with this pattern a bit, and I want to do so that they're kind of flipped. So there's a series of them going in one direction, and then there's a series that are going in another direction, right? Kind of like what's going on in this example. And I think there's just many examples like that have kind of flips. So let's talk about how to do that. This is where it's really important to think about the state of things. Okay, so we've created the cylinder, we've capped it, we've rotated it. Then I want to make a copy of it that's flipped, and so I would do that after I've done all this stuff, basically. Remember that all this. Turn all this off now. This is just about creating this one object that you're going to copy that's parametric. Okay, that's what that bottom half of the script is doing. So we can take that geometry, and we can take a plane, and again, you know, we can. So I want to flip it, and I think I actually want to flip it about the XY. That's the mirror plane. If you remember, like AutoCAD, right? Yeah. So that's the opposite of it. So I have one state of it that's in one direction, and I have another state that's offshoot from it that's flipped in the opposite direction. Okay. And so then I want to go back to my. And these are just points, right? I want to go back to these points that I have. And I want to distribute half of the coin to one side of them and half of the other coin to the other batch. So then I go through and I add a call pattern again. So this is where I do the checkerboard pattern. So I have false true. And what I'm going to do is, and I got to go back. So what I'm going to do is take all those points. And so now I've got, I need to go back. I have that bug again. I need to make these odd. There we go. Okay. True, false. And then I make a copy of this. And you go in. And you can actually just pick these up and pull them with the mouse and just flip them. So true, false, false, true. It's like Christmas. All right. Okay, so I've got those. And so now I've got two new sets of points. And so what I'm going to do is just pipe this in for instead of all the points, I'm only going to do some of the points. And so then I get all those on that row. Okay? This is where it's important. So again, I had something that I did, and I just like repeated it. I went back through the script, and I basically like did like an alteration to it in the middle of the script. I didn't just add something at the end of it. I went through and I cut it, and I kind of pasted something in there, right? So you do the same basic idea. So I'm going to take this Orient component, but instead the geometry is going to be this mirrored piece. And the target is going to be the other list. And so then I've got this pattern. And then I did something, and now I realized that with the things I have, there's geometry intersecting itself. It's no good. So what I could do is I could go back and dial back that radius a bit. Too much. So you build the system, warts and all, and then you go back and you play with it until it works. Like, there's a way to design this really smartly so that it always has the right proportion. But for now, like even for what you guys are doing, I think it's okay as long as it like works for you. Now I had this big gap in these things, right? So I probably need to add more rows to like close that in. Or if I want bigger disks, right? I need to make the rows fewer and make the disks bigger. Okay. But that's kind of this process that I'm taking you guys through here. So there, again, you have this idea that there's the distribution and the logic of that, like essentially dividing this up into two sets of points. And then there's also this idea of the object that you want to create. So you have this parametric object, and you can start from either end. But this is how you get them to kind of merge together. Okay. And so again, and then I made one state of it, and I made a modification of it. That's another important idea. Okay. So this is a pattern that you can use over and over again. These are all patterns that we've already seen before. Okay. Okay. So I want to show another version of something like this that I think might help you guys as well, and that's distributing geometry that you created yourself. Okay. And I want to start with an SDL line. An SDL line starts at a certain point, has a like a certain vector direction, and it has a length. So it's really useful actually, because sometimes we don't have 2 points that we can connect together to make a line, but we don't want a line to start and we want a line to grow from there, and that's what this is for. I'm just going to drop one starting at the XYZ 0, 0, 0. The direction in this case is going to be X. I'm going to make a line in this axis. And the length of this is going to be a number slider, basically. Let's throw 100 out there. Okay. And these are hard to see. So I'm just going to throw an endpoints on there just so you see what it looks like. Because it's actually on the axis. So it's hard to see, but you get a line between those 2 points. Okay. So this is a really good technique if you don't have a surface, right? If you don't even know how tall the thing is going to be, but maybe you want a line, or you know how long it's going to be. You can start by creating a line, or you can start by referencing a line. Okay. Then you can go ahead and divide that curve up into a series of points. Okay. So this is about distributing things along a line. The other one was about surfaces and distributing things in two axes at once. This example is just going to be a row of things. Some of you guys just have rows. They're not actually grids of things, okay? And so you don't need to worry about surfaces. So this is for you. So I go ahead and give myself some arbitrary number of points along that plane. So what's interesting about this is that I can change the number of points. I can also change the length of it. So the spacing comes from that. This is different from just a series. I know it looks like that right now, right? But the idea is that this is actually on any curve. Okay, that's the important bit of this. It just happens to be a straight line. And as I've said time and again, if we have points, we can distribute things. And so one thing that you might distribute would be geometry that you draw yourself. So I'm going to do a planar surface. And this is really geometry. You might reference it as a surface. But it can be anything. Geometry can be anything you make in Rhino that's one object. Okay. It can be trees. It can be little scale people. You can distribute geometry using the same ideas we have here. So I had these like fins that I made. Okay. And I can go through and using Orient, I can distribute them all on this line. Because again, this is not parametric, it's just some reference object. So I don't have anything I can plug into it to change its location. I could move it, but that doesn't pay attention to these points. So Orient is really the like tool for the job. So I start there. I need to, since it's actually centered on 0, 0, 0, an XY plane is fine for the original orientation. And then on my points, what I want to do, I'm just going to throw another XY plane out because I want to keep that orientation. So we distribute planes along the line, and then we plug it in for Orient, and we get a series of fins. Okay, and that's like anything that you can make already in Rhino. Like it's just you can just draw it. Okay, and that works, and that's parametric. Like as I increase the number of these things, as I change the spacing of these things. Okay. I can do the same thing that I did last time with the cull pattern and make some interesting forms by taking the list of points and dividing it up, and then using that to distribute my planes, and using that to orient these. So now I've got fins on half of them. Then I can go through and if I've referenced my geometry, I can go ahead and rotate just like any other geometry. And the base plane is going to be the same. And let's just say half pi is 128. So it's flipped. So I have a copy of this. Let's look at it. I guess it's not really flipped. All right, I'm just going to do a number slider. I'm not using the radians thing, but okay. Let's just do. This is bad form, but I'm doing it for speed here. Okay, flip it around the other way. Thereabouts. Okay. And so I have a copy of this. I have a different state of it. And what I can do is I can go through, make a copy of the orient component, distribute this geometry, and then I can go through this whole thing with the cull pattern again. Flip the cull pattern. Plug it in for the point. So then I've got something like this. And you could make something way better than that, but it's just the idea. So anything that you've got, you could do this with scale. The transform that you make could be anything. So they could rotate, they could get bigger, they could get thicker, they could move in and out from each other. Like you just make one row that's moved a little bit in the Y. In fact, let's just do that. Let's just move them.
So can I ask a question to
Yeah.
our project?
Yeah.
Are you wanting us to generate everything with Grasshopper, or are we also drawing shapes in Rhino? And then
It depends on what it depends on your project. I mean, sometimes the best thing to do is to draw the shape, and then the variation comes in the transformations you make to it. Other times you want to make the entire shape parametric, and I'll show an example of that next. Actually, that's where I'm going with this. But so I want to talk about another pattern that I've talked about a lot, which is that we talked about distribution. So here's a shift. I can shift these. Okay. So making objects parametric, distributing over parametric objects, but then also like once they've been distributed, transforming them somehow, and that includes having like a cull, so you can turn some of them off, scaling them like differently, rotating them like differently. Okay, these little like tweaks to it. Once you've made a lot of copies, you can then kind of vary them. Okay. And that's where a lot of your projects, like if you guys make the repetitive pattern on your building, that's the next tweak you can make, is to say, great, this is what this architect did. Now mine's gonna like shift in different ways, right? Like I'm gonna play with that a little bit. I'm gonna play with the spacing. I'm gonna play with that. So if I started off with just a row of these, now I've got these things that are kind of shifted. I've got these things that can rotate in different directions, and I can begin to play with that. And you could even go through with graph mappers and vary the variations on these things. So these things would get larger from sort of like a parabolic curve, right? Or maybe like there's a sine curve that lets them like move in and out like differently, okay? But the first thing you gotta do is like you gotta get this object distributed, okay? Okay, so that's a pattern for like a row with any kind of arbitrary geometry. This could be parametric too. You could substitute something for this geometry that's parametric. Okay, the last one I want to talk about may not apply to most of yours. I know it applies to one in particular, but I want to demonstrate it to prove a point about these patterns and how flexible they can be. So points, I'm really hung up on points because again, they're basically raw math. You know, they're just coordinates, but they're the genesis of like everything that we can work on, right? Points turn into curves, which turn into surfaces, etc. Okay. And so what I want to talk about really briefly is how powerful it is if you just parametrically associate points, okay? A square is basically 4 points, but the points are relating to each other, right? You have 2 points that are always above each other in the y, and 2 points that are always side by side in the like z, let's say, and then there's this other point that's a mix of the two, right? So there's only really 2 variables, and you can think of it as height and width, but it's actually just the coordinates of these points. Okay, we've used that rectangle object, which I really hate a lot. It uses like the 2 domains. You have to add all the crap to it. It doesn't work the way that I would like it to. But we can build our own using a series of points. And then I want to show you how powerful it is when you can modify those. So I'm going to take some number sliders here. And this is all stuff you know how to do. It's just that you haven't seen it configured in this way before. Which is why I want to bring this up. I want to destabilize your notions of what's possible here. So if I plug something into a single point, I can play with it in the z, right? So I have a point now that's in the z it's in the x that I can move. If I make another slider, I can plug it in for the y, and so now I can control the y of this point. It all starts from this point, okay? If I get creative with that, I can go through, and now if I want the point that's this corner here, I would just say that I want only the I want these to have the same x. So now I've got these points. And then if I wanted, this point, I would say I just want one that's working in the y. And there you go. I've got the points I need to make a square. So let's take the lines and connect them to each other and make our square. So we've got this line. And this is a little laborious to set up, but it's kind of powerful once you get to it. And I'll say this too: if you want things to cross each other to make x's or whatever, right? You just plug in the points in a different order. So this is a really useful pattern for that as well. Like that, okay. Okay, I might have made the same one twice. Okay. Okay, got those, got that one more. And I want this point to plug into that point. Okay. That's pretty easy. There we go. Okay, so I've got these 4 lines. I've got 4 points, 4 lines. If you want just that square, you could join all the curves together with a join component, and this is kind of like a loft. You just plug in things by holding shift. And now 4 become one joined curve. Okay, very unsexy. I just recreated a rectangle. But there's stuff you can do with it. Because again, now I have access to all these. This is actually kind of a hack too, because you guys don't know, we don't even talked about data structures yet, but this is a way to get access to these without knowing about data structures. So remember the evaluate curve? Of course you do. You can take a line. I need to turn hide join here, otherwise I'm going to take a line into it, and then T is basically from 1 to 0, 0 being part of the line, 1 being on the end of the line. I guess I plugged these into a weird order here, but you can get a point along a line. Okay? And so what I can do with this is I can make another point. So I've got this point that's along a line, and if I want to get the other point on the end of it, I can get the length from this, and that's the x coordinate for this other point. And then if I make another line, I can plug these 2 into each other, these 2 points I just made, and now I've got a line that's parametric along that length. Whoa, actually, that's awesome. I think I just need to flip the the order of these to make that work the way I want to. There we go. Again, accidents are really good. There's a great article by Greg Lynn about sort of like weaponizing accidents. I also like Bob Ross's like happy accidents. If you do things that are unexpected, they can be interesting. So again, if we're treating this, and this is parametric, so I can go through and I can add more space to this, and I can get a line, and of course you could get a line that's there in like the vertical, right? You could get multiple lines through there if you plugged in multiple values here. But I just want to prove a point with this thing that you can create these structures. And then what you can do with these is you can offset them. So offset works like AutoCAD, offset. So if I have a square and I offset it, I get kind of a border, right? That's where these can become. These can start to become surfaces. So I take my outer border and plug it in, and I can offset this by some distance, and then I can loft these together. So I take my outer curve and my inner curve, and I need to flatten these. That's what the bug is coming from there. And I get the surface. And then if I extrude that, in this case into Z, I get like a box, right? And I could offset that other line, and I could loft it, and I can extrude it, and then I start to get frames that are parametric. I could extrude at a different distance actually to get a mullion. Why don't I go ahead and do that anyway? That sounds like fun. Okay. So take this one, and this is all going to be kind of buggy here, but we'll fix it. So I've got this line that's an offset from that one. And the loft is going to be this line and the offset line. Do that. And then if I have a slider for the height, I can change the height of that. So I've got a different structure in here. Okay. So then I've got like a parametric frame. There's lots of different things you can do with that. You can experiment with series of points within this to create more complicated things. You could do series and then you could cull them. So this is now like a playground for this, right? You can do all kinds of things once you start, just by starting with a simple frame of points. Okay. There's a lot of variability with this. The next thing that I can do with it is create. So what I can do, and this is an important component too, is the group component. If I want to make copies of this, I don't have to go through all these different, patch cables and like plug them all in together. I can make a group, and that actually is going to keep them all together. So I can take the one extrusion and group it together with the other, and then now my group is all one thing, and I can start to move that, I can distribute that, I can transform that as one thing, as opposed to all the individual elements. Okay, so when you get going further downstream, it's pretty useful. I'm gonna go ahead and hide all this. It's too much information here. Okay, so I got a group, and I can move a group. Wait, not in Grasshopper. Move. And I'm going to move it in the X. And so you can see that I've already got that. But remember, we can repeat things by plugging in multiple values, so we have a series. And the step size, which is the distance we want to move each one in the X, is all the way over here. Because it's that X point. It's the edge of our thing. Okay. If I go through here and let's give it some number here. So once you have that object, copied. So this is instead of distributing it on some thing, we're using these as a module, and we're just copying those like modules. If I go back and I change the size of the original module, it's gonna, we're gonna take up less space. Then I can take this piece of it and move it into Y, another series. And I'm going to take, and now that is going to be the Y dimension. And I probably want a different ease. Okay. What's wrong with this one? Why isn't it a grid?
Because it's coming from that one square and not from the
Yeah.
group.
Okay. What's wrong with this one? There you go. So you have a parametric grid of these things. And you can take the stuff that I just showed you, right, and turn some of them off, distribute them into groups. You can do more than 2 cull patterns, like this whole kind of checker thing that I've shown you. If you get the pattern right with the true falses, you could do anything, number of things you want. You could also do like true, true, false, and then do false, false, true, right? So don't get stuck in that either, like with that pattern. What if you have 3 things that you're distributing along this in different patterns, okay? But so, you know, this could easily be used for some kind of an infill element as kind of like a facade study. Let's see here, but it's completely parametric. What's that? Yeah, it's about to freeze. Is right. It's painful. It's actually not oriented upright, but you get the idea. So there's a few patterns that I think can kind of help us with the assignment. Again, there's different ways to attack this problem. You can attack it from the bottom up, like from playing with the module itself and experimenting with the module and trying to, you know, like, and then making that like a distribution. But the problem with that is that then it's like dependent upon the module. Sometimes that's what you want. Like if you're going to manufacture a unit like a cinder block or something like that, your building's based on that module. Another way to attack it is to start from the target, start from the surface and work your way like backwards. Use that to generate your object, right? And that works differently for your projects. Okay, that's kind of a top-down approach. But always when you're working, you want to continue to refine your idea. Start from, you know, just get something to work. Don't move on though until you've understood that one piece of it. Okay, so don't just keep slapping components on. The further away that you get from it, if you haven't fixed it, if you haven't understood it, you won't know where your bug is. Okay, so get something to work by refining it. Add another thing, look at that some more. Add another thing, keep refining it, but don't go too many. Don't take too many steps ahead of yourself. Okay, I make this look really simple, but it. All right. I butt dialed my voice phone. Okay. So yeah, when I make these designs for these, it takes like a while because I'm like plugging things into the wrong things, and you know. But it's like you gotta figure out how to get that, like the points to be where they need to be first. Then you figure out where the lines need to be, and you don't keep going on until you've isolated that piece of the problem. Okay. Even with a plan, you want to make sure that you understand each phase of it. Then you can always go back and you know, change things and play with things. Okay, so a lot of these patterns are, I mean, none of this stuff, other than the solid stuff I showed you, are things that we haven't seen before. It's just a matter of being kind of clever with them and the you know, the specific context that you're like applying them in. So that's why this is great that we each have a different project, and there's going to be different ways that each of your groups are going to address the project. There's no like right way to do it. The goal is just to get it done and then to see what your method gives you in terms of the variability that you make. That's why it's going to be interesting to see each group's take on it. I highly doubt that each group is going to do it in the same way, because there isn't like one perfect way to do it. Okay. Okay, so this is going to go online later today. I have to encode it. Does anybody have any questions on this stuff? We have like a few minutes. Did everybody get some inspiration though? All right. All right, I'll see you guys.